Hello, you are about to receive a 15-minute introduction to astronomy and the ABCDs of astronomy. And ideally, you should learn it from me under the stars and a little bit slowly, but this is going to be a very fast crash course and you're going to learn a lot. So, buckle up. So, this is the view of the sky that I would see right now, and the sun is at the angles and everything is perfect. This app simulates it everything perfectly. First of all, of course, you have the horizon and you have the zenith, which is the topmost point, and I could show you like this is the topmost point. You could imagine that for every person on the surface of the earth, the topmost point is in all the directions, so there is no universal topmost point, but then there is a universal point that all of the observers on the earth could agree on. They could point at the same point, like decide and then point at the same time, and then all of them would be pointing towards the same star or same point, and that point is the North Star, and this is the different coordinate system, which is a better one. And here you see that this is the North Pole, North Celestial Pole. And what is this is something you first have to understand about astronomy, that this is the most important part of astronomy. The earth rotates, or from the perspective of the earth, the stars rotate and the sun rotates around the earth. And now let me make it go into evening, and notice that the sun, it does not set. So I ask this question every time that I teach astronomy. Okay, so I'll remove the grid so it's not obvious. And if when I ask this question to people, how should the sun set, they say that it should set vertically like this, but it does not, and at least in where I am, and you would see why not. But when I put this, then it's obvious that it would not. Okay, so let me move. So sun actually sets at an angle, and notice that it is not setting at the west, it's setting south to the west, and that has to do with the fact that it's winter in the northern hemisphere. So by that, looking at that, you can tell where I am. Okay, so now you can see this thing, that there are stars in the sky obviously, and they don't change their positions. They are very rigidly fixed. Their angles between them and so on, they're very rigidly fixed. They don't change their positions, and they rotate in unison. So so let's see, I will put the grid on so that you can, no, not this grid, and let's yeah. So you could see that the entire sky rotates, and that's the first clue that it's a bigger assumption to assume that the entire universe rotates around us, so it's better to assume that the earth is rotating, and that's what's happening. The earth rotates and we feel like these stars are rotating. This is the first lesson which actually even I was not aware of until I started learning astronomy a little bit professionally, or as an amateur in the astronomy club, because I thought that the stars were just sitting there. It had never dawned on me that they also rise and set. So this is the first thing that they do, they rise and set. And this is called the celestial sphere. You could almost imagine that there is a sphere, and on which the stars are fixed. Now see that the sun did not rise to the east, but it rose to the south of the east, which is interesting because not only does it rise south to the east, it also sets south to the west. So it actually traces a smaller circle. Now what happens as we go to winter? So first thing with astronomy is learning the sun's movements. First object, the most important object, is learning about the sun and the moon. So let's start there. Now this, you saw this happening, so let me pause it. I mean, not pause, play it on the current 1 second per second time, speed of time. And now let's, what we could do is we could go to summer, which is okay, you could see that, you saw that I went to June, right, and the sun climbed up in the sky. So on the 6th of June, sorry, on the 21st of June, which is the longest day of the year for people who live in the northern hemisphere, work it out why. No, not right now, but maybe later after the video is over, maybe you can work it out why. I mean, why is it in the south that 21st June is the longest night and not the day? Anyway, so let's focus here again. You can see that the sun moved here, and now it rises and sets from northern to the east and west. So now it's tracing a much bigger circle. Let me show you. So see, it rises beyond north in the and then it traces a much bigger circle, so it's longer in the day. as compared to, for example, if I can change that as it goes along. So currently it traces a much smaller circle, and you can imagine the celestial sphere, right? And you can imagine that so next month it would be here and it's tracing a bigger circle, and so on and so on. And on the 6th of uh, 21st of June, you would have it trace the largest circle, and on the 3rd, you would actually have it rise exactly at east and it set exactly at west. That's called an equinox, because equal nox night. So it's the day when 12 hours of our day and 12 hours of night we have. There are some complications there, but it's out of the scope of this video. So let me go back to the current time. Okay, so this is what it is right now, and we have learned a lot already. You have learned that the sun doesn't set in the west. So for example, we could make it set a little as today, and now I'm going to change the time, and you could see that each month, like it's currently moving towards the north. In Sanskrit it's called Uttarayan, and around 21st of June it turns back. It's called solstice because the sun stands still. Actually we can go near that date and see why they say that. The sun travels to the north, and then for these days it's almost as if it's just there, and then it starts moving back, and much faster and faster. It's something like the simple harmonic motion. And then when it's around September of 21st, then that's when the other equinox comes, the September equinox, and then it moves very fast every day. And after a while, at the same time, you wouldn't even see it in the sky. Okay, now let's go to the other part of the uh, how this changes for us, right? Because this is the length of the day, as you know, as you go towards the north pole or the south pole, it changes drastically throughout the year. You know that there is this Arctic Circle, like some parts of Norway and Chile and Antarctica, and in there, if you are there, then you can have a day like 24 hours of sunlight. And why is that? So let's and also on the equator, the length of the day never changes, and so let us study why that is. Now we can change the position here. Hold on. Oh, it was the first window, and I can go north like this. Right now I'm in Siberia, and you can see that uh, the North Pole has moved up quite a bit, and we can put the other coordinate system to see that okay, it's still not to the extreme north. And then we can also go back and go as much north as possible. And currently, since it's winter, you don't even see the sun. uh, it's 24 hours of night time there. But why not actually just go to North Pole? Give me a second. So now we are at the celestial North Pole. I mean, it's a point on the Earth where the point about which everything rotates is directly overhead. You can imagine you are walking. This is north for me, and if I start walking in that direction, the North Star would start rising and rising, rising and rising, rising and rising until a point where it's on my head. And if I keep walking even further, it would fall behind. Uh, so that's the North Pole. And on the North Pole, you have stars going in circles like this. So see, and we can go a little bit ahead in the date, so you can see how it looks like in the summer for the northern hemisphere. And you can imagine that if the sun looks like this in the northern hemisphere in June, then in the southern hemisphere they can't see the sun at all. It's completely blocked by the earth. So in the southern hemisphere at the same time, the sky would look something like this. In the southern pole, not southern hemisphere. Okay, now since we have not a lot of time, we have 5 more minutes, so I will explain what the things here mean. So for example, if I select a star, then you have to know what all of these things are, and let's spend some time talking about it. Okay, so firstly the name. The name of the star, it's a given name, it's called Capella, and a lot of the stars have actually Arabic names. It's historical, and all of the other names that you see here, they are not like, this is not one entire name. These are different names for the same star depending on the survey and so on. So let's begin with the Capella, which is the English name, and then there is some Arabic name which is Al Hajot. And goat star, if it, there are this daemon star and goat star and dog star and so on and so on. Alpha or means, alpha is the first letter in the Greek alphabet, right? So alpha is the brightest star in Or, which is Auriga. So if I turn on the, yeah, this is Auriga, and this is the brightest star in Auriga. So beta Auriga would be probably Aldebaran. Let's see. Yeah. Oh, this is okay. This is a Taurus. This is another constellation entirely. So maybe this is beta. Yeah. This Menkalinan is the beta Auriga, which is the second brightest star in the constellation of Auriga, and Alpha Auriga is the first one. If you don't need, I mean, given names, and for the popular stars we can refer to them by the given names, and for the stars which are part of a constellation diagram like this, we can refer to them by alpha, beta, and so on. And then if you have some random star like this is still tau Auriga because inside the Auriga, but we can go even like a very small insignificant star. This is a real star. I mean, Stellarium doesn't put just random stars out there, it's a real star. And okay, they haven't given the name of it, so it's too insignificant for them to, yeah. So if this star, it's a I mean, you can't name every star. So there are these satellite surveys that just survey the sky, and these are, so this is the HIP, this is the Hipparchus survey, and in the Hipparchus survey this star is named index 26249A, right? And then there are other surveys, and this is what the other names are. Now this is a double star, which means that it's two stars actually, not a single star, but then you can't see it from the earth. I mean, the stars are extremely bright and extremely small, so when they are together and so far away, they just look like one. And I will not go into how we know that. How long? 3 minutes, okay. So magnitude is 0.05, and there's a lot to talk about here. Magnitude is how bright the star appears, but it's something like the classes of stars. So imagine that the magnitude 0 star are the brighter, the magnitude 1 star are also brighter, but then magnitude 6 stars are the dimmest of stars, which you could see barely with your naked eyes, and 7 and all you would not be able to see. So that's what magnitude is. The smaller the number, the bigger the brightness. When it comes to eyes, like perception, it's just that the magnitude 6 star is 6 times dimmer than the magnitude 1 star. But when you talk about capturing the flux on a camera or a sophisticated astronomical device, then that's actually not 6 times, but a difference of 5 magnitudes. So the difference between the 1 and the 6 time is difference of 5 magnitude. That actually corresponds to a difference of 100 times difference in brightness in terms of numbers of photons received on the receiver. It's a logarithmic scale, and Jupiter is one of the brightest objects in the sky, and it's in negative because it's too bright to be a star. So the brightest star in the night sky for us is Sirius, and that is, oh, it's still in negative. Okay, let's talk about other attributes here. Absolute magnitude is the magnitude of a star when you are at a fixed distance, I think 10 parsecs from it. Color index is, let's not go, not very important. It's about how red and how blue a star is. And I already talked to you about the coordinate systems, but let me just quickly recap them. This coordinate system is called the altitude azimuth coordinate system, where you mention how far the star is from the horizon to the zenith in degrees, and then how far it is from the north along the horizon. So that's this star in particular is 99 degrees from the north and 46 degrees up, like this. R angle and declination, or right ascension and declination. Okay, we are at the north pole, and this is why the sky looks so weird. I mean, I'm not used to the sky like this, so let me go back to somewhere in India. Okay, and let me remove atmosphere. uh, and let me get rid of this coordinate, put this coordinate system. Okay, so here the angle starts, it's like the spherical coordinate system where the pole is the north pole, and then you measure the angle along the north pole to the south pole. It goes from 0 to 180, and the other angle you measure along the azimuth, and we have chosen the 0 of azimuth to be where the earth's like the north pole, the rotation vector points to in when it's at a vernal equinox. Doesn't matter, it's a random point, not a it's a special point, but it's arbitrary. Okay, now we have the galactic coordinates there with respect to galaxy, and then there is solar. So I will ignore the coordinates, and then let's see, right? This is all understandable, right? When it rises, when it sets, and so on. And the distance, yes, it's 42 plus or minus 0.26 light years away, which is relatively close, not as close as Sirius and other stars. The closest star is 4 light years away, and yes, and then you have proper motion, which is it all the stars. I did say that they are fixed and they don't change their motion, but they are, all of them are moving in like just moving around. So if you wait for 1 lakh years, the constellations would look very different, and you could do that on Stellarium. Why don't you? And so I don't have time to go into parallax and spectral time because we are already out of time. So I will end here, but I will actually, this was not like a comprehensive overview, because obviously in 15 minutes you could only teach as much. There is so much, we didn't cover planets, and this is something very important, and I will just show one thing about planets that is very interesting and people may not know about it. First let me get rid of the ground, and now we'll center on Mercury and just look at how Mercury moves in the sky, right? Uh, hold on, this happens when you are okay. Now you can see that Mercury currently, oh no, not Mercury, I wanted Mars. Where is the, okay, okay, now this is too fast. See that this Mars is moving in the sky. Oh, okay, oh, okay, it's moving in the sky, but it doesn't move like the sun or the moon around the earth. It will do something very interesting. Moon goes in a perfect circle, I mean an ellipse, but see what Mars would do now. See, it stopped. Now it does something weird, goes back. It's called the retrograde of Mars. This is very strange. Moon doesn't do that. What is this? And I have actually observed this. It actually doesn't take a long time, just a couple of months to observe this whole retrograde motion happening, and I encourage you to do that because Mars is bright enough that you can even observe from the big cities, and that is called the retrograde motion of Mars. And let's just admire the view here, because we know that, so let's just focus on the sun. So you can see as if we are going around the sun, and you could see the environment that we are living in. Oh, I forgot that when I record the names and it gets a little bit blockier, like this gets blurry and pixely. Okay, so you could see as if we are moving around the sun, but we are looking at the planets and everything go around. This is our view from the earth, but since the earth rotates so much, it's very annoying. So see, it actually looks more like this and also this, if you looked at that scale, but otherwise this is what Stellarium allows us to do. I like this view a lot, and I can just keep looking at it, earth going around the sun. But from the perspective of the earth, it looks like the sun goes around the earth. And okay, I will not tell you how we finally proved that the earth is the one that moves, but then that creates a bigger problem. If earth moves, then why don't we feel anything? And that's where Galileo comes in. Okay, enough for today. It's already almost 20 minutes and I'm off my promised time frame, and I have not taught everything that I wanted to teach you in this video, but I really expected too much of myself. So thank you for watching.